All right, let's jump right in. We're going to explore how some of the strangest, most mind-bending rules in all of physics ended up creating two things we absolutely can't live without today: lasers and fiber optics. It's a wild ride from pure theory to incredible tech. So here's the big question for today. How on earth does a tiny, totally unpredictable particle have anything to do with, well, the entire global internet? It seems impossible, right? But the answer is this amazing story of scientific genius that literally changed the world. You know, back at the end of the 19th century, physicists kind of thought they were done. They had classical physics, this perfect, predictable rulebook. You throw a ball, you know where it's going to land. Simple. But then they started looking at the really, really small stuff. And that beautiful, tidy rulebook, it got completely torn to shreds. And that brings us to our first part, when physics broke. This is all about how a few super stubborn experiments just shattered everything we thought we knew about reality. So imagine you're a scientist back then. You've got these experiments, like the photoelectric effect, that just refuse to make sense. The old rules said if you shine even a dim light on metal long enough, it should build up enough energy to kick an electron out. But that's not what happened. It was like the universe was playing by a different set of rules at this tiny scale. It became obvious the old physics was broken. We needed something new. And that something new came with the weird quantum rules. And when I say weird, I mean really weird. These weren't just tweaks. This was a total rewrite of how the universe works at its core. Okay, first up, wave-particle duality. Get ready for this. The idea was, what if things aren't either a wave or a particle? What if they can be both? So light, which everyone thought was a wave, can act like a little bullet of energy, a photon. And an electron, which we thought was a particle, can act like a wave. It all depends on how you look at it. Wild, right? And then there's the famous uncertainty principle. Werner Heisenberg figured out that in this quantum realm, you can't have it all. There's this fundamental trade-off. The more you pin down a particle's exact location, the less you can know about where it's going. And the other way around, too. You literally cannot know both things perfectly at the same time. And check this out. This isn't because our measuring tools aren't good enough. This little formula right here shows that this uncertainty is baked into the very fabric of reality. It's a law of nature. There's a fundamental fuzziness to the universe. We had to say goodbye to perfect certainty and hello to a world run by probabilities. So we've got these bizarre, abstract rules. What do you even do with them? Well, it turns out you can use them to build one of the most incredible tools ever invented, the laser. And yeah, that stands for light amplification by stimulated emission of radiation. To get how a laser works, you just need to know these three ways light and atoms play together. First, an atom can suck up a photon and get all energized. Then, it can just chill out on its own and spit that photon back out in some random direction. That's spontaneous emission. But the third one, this is where the magic happens. It's called stimulated emission. If a photon flies past an already energized atom, it doesn't just pass by. It stimulates that atom to release a second photon that is a perfect identical clone of the first one. And that right there, stimulated emission, that is the whole secret. That's the key. One photon goes in, two identical photons come out. Those two hit other excited atoms, and now you have 4, then 8, 16. You see where this is going? You get this incredible chain reaction, this avalanche of perfect cloned photons. That's the light amplification in laser. And the light that comes out of this process is just different. It's not like the light from a light bulb, which is just a messy jumble of different colors going everywhere. No way. Laser light is hyper-organized. It's a super tight beam. All the light waves are marching in perfect formation. It's one pure color, and it's incredibly intense. Okay, so how do you actually build one of these things? You need a few key ingredients in your recipe. First, you need what's called a population inversion. That just means you need more atoms that are excited and ready to go than atoms that are just sitting around. To do that, you use a metastable state, which is basically a special waiting room where atoms can hang out in their excited state for way longer. Then, you just stick some mirrors on either end to bounce the photons back and forth, building up that chain reaction over and over again. So the first laser was built way back in 1960, but of course we haven't stopped there. The technology has kept getting better and better, which leads us to the absolute cutting edge, the ultimate laser powered by quantum dots. So what is a quantum dot? It's a tiny, tiny crystal, a nanoparticle, just a few nanometers across. We're talking like a few dozen atoms. It's so small that the weird quantum rules totally take over, and it starts acting like a single, giant, artificial atom. And the coolest part? We can tune the color of light it emits just by changing its size. A little bigger, you get one color. A little smaller, you get another. It's incredible. And putting these quantum dots into lasers, whoa, it gives us some huge advantages. They're way more efficient. They don't care as much about temperature changes. They can be switched on and off at super high speeds. And like I said, we can get a whole range of colors just by cooking up different size dots. This is a massive leap forward. All right, so now we have this perfect, ultra-controllable light source, thanks to quantum mechanics. Awesome. But what good is it if you can't send it anywhere? And that brings us to the last piece of this incredible puzzle, guiding that light with glass.
Think about the problem. We've got this perfect beam of light. How do you send it across a city or under an ocean without it just fading away or getting lost? The solution was as brilliant as it was simple: the optical fiber.
Now, optical fibers work because of this really cool physics trick called total internal reflection, or TIR. It's amazing. Basically, if you shine light through a material, say glass, and hit the edge at a shallow enough angle, the light doesn't escape. It reflects back inside perfectly. No energy is lost. It's like a perfect mirror, but without the mirror. And the way an optical fiber is built is just genius. It has this inner core made of super pure glass. Then it's wrapped in an outer layer called the cladding, which is made of a slightly different kind of glass. This tiny difference in their properties is what creates that perfect mirror effect. The light hits the boundary and just keeps bouncing its way down the core, trapped inside, for miles and miles. And this formula for what's called the numerical aperture is super important. It basically tells us how good the fiber is at gathering light. It defines the size of the cone of light that the fiber can successfully trap and guide. The bigger the NA, the wider the cone, and the more light you can cram into it. And just like that, we've connected all the dots. It's an incredible story, right? We started with a quantum mystery, we figured out how to harness a weird quantum rule called stimulated emission, and then we learned how to guide that perfect light through tiny threads of glass. And in doing so, we literally built our global network. I mean, think about that. We used these bizarre, counterintuitive quantum rules to build the internet. It's just an amazing journey from pure, abstract science to world-changing technology. And it really makes you wonder, doesn't it? What's next? What other weird quantum rules are just waiting for us to figure out so we can build the next amazing thing?